All right, if you're getting ready for a software design interview, there is one principle that can totally set you apart from the competition. Today, we are cracking the code on the dependency inversion principle. You know the feeling, right? You build something, it works perfectly, but the second you need to change one tiny piece, the whole thing just crumbles. That's what we call tight coupling, and honestly, it's a developer's nightmare. But what if I told you there's one single principle that could fix all of that, making your code flexible and ready for the future? Well, that's where dependency inversion comes in. It's the D in the famous solid principles, and trust me, it's a game changer. Once you really get this idea, it will completely change how you think about connecting the different parts of your software. So, what is it really? The official definition has two simple rules. First step, high-level modules should not depend on low-level ones. Just think of it this way. Your main application logic shouldn't care about the tiny details, like which specific database you're using. And the second part, which is absolutely key, is both should depend on abstractions. Now, an abstraction is just a fancy word for a contract, like an interface that says what something does, but not how it does it. If that formal definition feels a little academic, don't worry. Just burn this one simple phrase into your memory, because it's the heart of the entire principle. Depend on abstractions, not concrete classes. This is your new mantra. Instead of your code depending on one specific, concrete thing, it depends on a general contract. To make this crystal clear, let's step away from the code for a second and use a real-world analogy that I think you'll get instantly: a simple light switch and a light bulb. Okay, so imagine a really bad design. A light switch is literally hardwired directly into one specific model of a light bulb. The switch's entire purpose in life is tied to that one bulb. It can only turn that single specific bulb on and off. In the coding world, we call this being tightly coupled. So what's the big deal? Well, what happens when that bulb burns out? You have to find the exact same model to replace it. And what if you decide you want to use that switch to power a fan instead? Nope, can't do it. You'd have to literally rip the switch out of the wall and rewire everything just for the fan. It's totally inflexible, and it's a massive pain. So how do we fix this mess? We use the brilliant design that's already in our homes. The switch isn't wired to the bulb itself. It's wired to a universal socket on the wall. That socket, that is our abstraction. And this perfectly illustrates the good design. The switch, our high-level module, doesn't know about bulbs or fans. It only knows about the socket, which is our interface. And the bulb and the fan, our low-level modules, are both designed to plug into that same socket. Now you can plug in a bulb, a fan, a vacuum cleaner, whatever. The switch never has to change. That right there is the power of depending on abstractions. Okay, the analogy makes sense, but how does this actually look in our code? Let's take what we've learned from our switch and bulb and apply it to a real software application. All right, let's check out the code side by side. Over on the left, you see the bad design. See how the switch class is directly creating a new bulb object? That hard-coded dependency means that switch is forever stuck with that bulb. But now, look at the good design on the right. The switch class doesn't even know what a bulb or a fan is. Instead, it just depends on a general device interface. This means you can give the switch any object, as long as that object promises to act like a device. We often do this with a pattern called dependency injection, where the device is just handed to the switch. And just like that, our switch is completely decoupled and super flexible. So why do we go through all this trouble? Is this just some fancy theory? Absolutely not. Understanding this is critical for any serious software project, and it's exactly why interviewers love to ask about it. The payoff is huge. First, you get flexible code. Just like swapping the bulb for a fan, you can swap out a MySQL database for a PostgreSQL database without rewriting your entire application. Second, it's easy to extend. Need to add a heater? No problem. You just create a new heater class that follows the device rules. The switch code doesn't change at all. And finally, it makes testing so much easier. To test your switch, you don't need a real complicated bulb. You can just give it a simple, fake, mock device. This makes your tests way faster and more reliable. So what are the common traps to avoid? Well, they're the exact opposite of the principle. The number one mistake is creating direct dependencies on concrete classes. That's our new bulb example. And the second is just forgetting that abstractions like interfaces even exist. You should always be asking yourself, could this specific part change in the future? If the answer is yes, you should probably be using an interface. And if you want to sound like an absolute pro in your next interview, here's the line you need to remember. When they ask about dependency inversion, you can confidently say, The core idea is that high-level modules, the ones handling the business logic, should always depend on abstractions, not on concrete low-level implementations. This decouples the entire system, making it way more maintainable and flexible in the long run. And that is the dependency inversion principle in a nutshell. It's a mental shift, really, from thinking, how do I connect this thing to that thing, to how do I create a universal contract that they can both agree on? If this helped you out, make sure you subscribe because we are covering all of the solid principles in this series. Now think about it. What part of your own code could you refactor right now using an abstraction? I'll see you in the next one.